Hello, this is Mr. Gilmore with the 5.6, the Hinge Theorem and its converse lesson. Now, we have looked at comparing angles within one triangle. The question today is, can we cross-compare triangles, such as comparing sides and angles between two triangles? A quick reminder before we jump too far into today's lesson. We have a property with our new relation of greater than, the transitive property. So transitivity of greater than is one of our new properties we saw earlier in the chapter. I want to remind you of that today because we're going to see this guy used again, that if we are working with three quantities such that A is greater than B and B is greater than C, that in fact A will be greater than C. Now, I wish to warn you here on this next slide. So be very careful. There's an error that's being made here in this slide. So someone might claim, hey, take a look at side CD, it's 3.16, and take a look at side AB, it's 2.83. Well, obviously, this side FD is greater than side AB, which then means the angle opposite must be greater. So we can claim that angle C is greater than, angle E is greater than angle C, right? Because that's the side, that's the angle opposite. And we have proven that the angle opposite the greater side is the greater angle. But there's a mistake here, okay? The mistake is this, that the anisosceles triangle theorem and the converse of the anisosceles triangle theorem, those are rules or theorems for just one triangle. That works within one triangle. We cannot cross-compare between triangles. In other words, if we take a look at these two diagrams below, here's a counterexample of you can't just claim that if one side is greater than the other, then obviously the angle opposite is the greater angle. Well, here's a counterexample below. These two triangles below are actually drawn to scale, which means the angles that do look bigger than the other, that is true, okay, because these are drawn to scale. So take a look at angle B. We're going to compare angle B to angle F. Look at this tiny little angle down here. Well, let's compare their sides opposite. The side opposite B is only 1.6, but the side opposite of angle F is 3.38. So obviously, the angle F should be greater than angle B, but it's not. Okay, that's a counterexample to this cross comparison between triangles. So why are we talking about this? Well, because we can cross compare between triangles, however, not in any case. We have to have some special relationships between the two triangles in order for us then to compare cross angles and cross sides. Where if I want to claim one side of a triangle is greater than another side of a triangle, then there has to be something that happens between those two triangles first. There has to be special things going on, special relationships, in order for me then to cross compare. And that's going to lead us into our two theorems today, the Hinge theorem and the converse of Hinge theorem. Let's talk about the Hinge theorem first. You're going to note that it is a longer conditional, only because we have to make sure we set up all of the certain properties that we need between the two triangles in order to cross-compare. Let's take a look at this first conditional here of Hinge theorem, and let's pay close attention to what's in the given. So let's take a look at the given first. If two sides of one triangle are equal to two sides of a second, so pause there for a second. Already we know that there's already a connection between the two triangles, that there are two sides of the first equal to two sides of the second. Let's see what follows. And the included angle in the first is greater than the included angle in the second. So notice there's three things going on already in this given. We already have two sides of one equal to two sides of the other. And there's a comparison of the included angles. These are the angles sandwiched between the pairs of given sides. So it can't just be any pair of angles, it has to be the pair of angles sandwiched between the pair of equal sides. So if two sides of one triangle are equal to two sides of the second, and the included angle in the first is greater than the included angle second, then, here we go, here's our conclusion, then the third side of the first is greater than the third side of the second. We can then cross-compare sides if all three of these conditions in the given are met, that you have the two sides, right? You have the one pair of equal sides, a second pair of equal sides, and this third thing that happens, which is a comparison of the included angles. Let's take a look at a diagram that brings the Hinge theorem to life. So here's actually what we're going to be working with. This is kind of our setup of our proof. We'll see actually the proof here in just a moment of the Hinge theorem, but consider this the setup. So here are our two triangles, ABC and EDF, or ABC and DEF. We're given already the three conditions that we need in the given of the Hinge theorem, which is that there are two sides of the first equal to two sides of the second. So AB is equal to DE, and BC is equal to EF. That's two sides of the first equal to two sides of the second. And we're comparing, we already have a comparison of their included angles, angle B and angle E. Okay, you see that angle B we're given is greater than angle E. That's in the given. Then what may we conclude? We may then conclude that the side opposite of angle B is going to be greater than the side opposite of angle E. In other words, that AC is greater than DF. Now, we're going to prove this. And I'll warn you, the Hinge theorem is a tricky proof. Okay, where we begin in this proof is with it's a construction. It's a little bit of a complicated construction. I'll explain it along the way. And then once we get through the construction, we're going to dive into the proof. And the proof is a bit lengthy. And because it's lengthy, because it's tricky, I've made this guided. Okay, I'm going to guide you through this proof. In other words, I'm going to walk you through the statements. You tell me the reasons why. So let's dive into our first part of this proof, which is the construction stage. So here's the strategy. Okay, we need to first form a connection between these two triangles, ABC and DEF, which means this. We know we can measure and make measure. Okay, so I'm going to measure angle B. Now I know that angle B is given to me as greater than angle E, which means I may construct an angle that will be greater than angle E using the vertex E. So what I do is I come over here to my triangle DEF and I construct this angle here. Okay, I construct an angle using side DE and this new segment here, EG. Okay, so this is kind of a ray shooting out here, EG, and I'm going to measure that angle here in B, and I measure this angle over here with this new segment, and I'm going to call those two angles equal. I can do that right off the bat, okay? I can measure and make measure. That's my prototype postulate with angles. Now, this segment, this ray that EG kind of shoots out of, I want EG to be of a certain length, okay? So notice then what I can do is, again, measure and make measure. I measure my segment EF, okay, which is the side of my original triangle DEF. And I want to duplicate that measure. That's why along this new ray that we formed with this angle, DEG, that we truncated it at that point G. Okay, so we stopped down here at point G, and we made it so that these two segments here, EF and EG, are equal in length. Okay, which then also means EG is also equal to BC over here. So notice that all three of these segments here are equal in length, right? BC, EF, and EG. Okay, so now what do we do with that? Okay, now that we've got this angle and this new segment created, EG, what are we going to do with that? Well, we're going to connect point G to a few things, okay? So let's connect a point G to a few things. So we then connect our point D, which is given to us, to point G. Okay, so it forms this segment right here. Okay, this segment right here. We get segment DG. And we already had point F laying around. Let's also connect point F to G. And what that does is, if you notice, we form a new triangle down here. That is going to be our main focus. That's where our main focus is going to lie, within that triangle. However, to get to some of the relationships we want inside that triangle, we're going to be working with several other triangles in order to get to that one, this bottom triangle, DGF, okay? Because here's what I want to prove. I want to prove that this angle here, DFG, is greater than this angle here, DGF, okay? I want to prove that those, I want to get to that conclusion that angle DFG is greater than DGF. If I can get there, then we've pretty much then proven the Hinge theorem, okay? And again, it's a tricky proof, which is why it's guided. Now, this is a long proof, which is why then on the next several slides, we have the proof laid out. So on the next slide, I have the guided part 1, which then follows into the guided part 2. Let's jump into this. So after our construction, post-construction, here's what we know. We know that the sides BC, EF, and EG are all equal, okay? We know that. And we know that the angle B here is equal to the angle DEG here. We constructed it that way, okay? That those angles are equal in measure, okay? So now let's jump into our proof. Let's start off with one of our very first triangle relationships that we're going to form between these two diagrams here. So immediately I can claim that triangle ABC is congruent to triangle DEG. Take a look. Triangle ABC, this first triangle, is congruent to triangle DEG. Why is that? Well, think about it. We were given that two sides of one triangle are equal to two sides of another. In other words, we know that AB and DE are equal, and that BC and EG are equal. That's two sides of one equal to two sides of the other. And we constructed it such that the angles between are equal in measure. Hey, we have triangle congruence there. That is by our side angle side congruence, that those two triangles are congruent. And now that we have congruence, we can invite our best friend to the party, which is CPCTC. I can claim then that AC and DG are equal in length. I can claim that. CPCTC. Now, one thing I wanted you to do, because we're going to change slides here in a moment, is I want you to mark that step here in your notes, okay? Because that step right there is going to come up again, but we're not going to see it until the very end of our proof, okay? The very, very end. So hold on to that because that's a necessary step that we need, okay? Just want to make sure we have that step in there until we get to the very end. We can use that. So we know that AC and DG are equal in length. All right, now we turn our attention to another triangle pair, okay? Let me move those out of the way. Take a look at triangle EFG, okay? EFG, over here on the right, EFG. Notice something special about that triangle. We have two sides of that triangle equal, which means it's an isosceles triangle. I can claim the base angles of this isosceles triangle equal. Why? Because of the isosceles triangle theorem, something we proved way back in chapter 3, okay? Now, we're going to focus on those two angles there for a moment, okay? Let's first, we're going to actually focus in on one of our angles here, DFG, this angle right here. Notice that angle DFG is actually cut up into two subangles. Let's then state that we know that DFG is equal to the sum of those two subangles, DFE and EFG. Why do we know that? That's the angle addition postulate, okay? We're allowed to add the two subangles together to equal the whole, okay? Which means, if that's true, I can claim that DFG is greater than any of those two parts, any of those two subparts. And I can claim that by the definition of greater than, that the whole is always greater than the part. Okay? So DFG is actually going to be greater than this angle here, EFG. And that's the one I want to pick on because it's in relationship to angle EGF. So we know this whole angle here is greater than EFG. But then we also know, since it's greater than EFG, whatever is true about EFG is going to be also true about EGF. Why? Look at step C. EFG is equal to EGF, which means whatever is true about the base angle EFG is also true about the base angle EGF. So I can claim then that the angle DFG is greater than the other angle EGF because of substitution. I can take EFG out and put EGF in. Okay, I could take that out and put EGF in. Alrighty? So that's by substitution. Now our proof is going to continue on to the next slide. What I'm going to do, one thing I want you to do is remember mark step B. Okay, I want you to look back at step B here in a moment. So make sure you mark that. But I'm going to carry our step F onto the next slide. So remember, because step F is another key step in our proof. Okay, and I'm going to carry that one over to the next slide where we're going to finish our proof off. Okay, so now we have this comparison between angle DFG and angle EGF. All right, so let's move on to the next slide and take a look at how our proof is going to end. So I carried step F over, okay, and we had the same reason, substitution, okay. So by substitution, we know that we have angle DFG greater than angle EGF, okay, we have that. Now let's focus on angle EGF for a moment, because EGF is also cut into subangles, which means we know that the measure of EGF is equal to the sum of both of those subangles. And we can say again that is true by the angle addition postulate, okay? That EGF is equal to the sum of EGD and DGF. Now, if you remember, DGF is one of our other focused angles, which is why in the next step, I claim that angle EGF is greater than its part, DGF. So I can claim it again greater by the definition of greater than. Okay, so I have EGF is now greater than DGF. That is another component in our proof that we desperately need, because here's why. Take a look at step F and step H. We can put those two statements together, okay? Because remember where our focus is. Our focus is we wanted to move to this triangle here, DGF. Okay, that triangle DGF. Well, I wanted to show that angle DFG is greater than angle DGF, and I can do that now, because take a look at step F and step H. In step F, DFG is greater than EGF, and in step H, EGF is greater than DGF. That right there means I can claim that angle DFG is greater than angle DGF, and why? That's our transitivity of greater than. If A is greater than B and B is greater than C, then A has to be greater than C. If DFG is greater than if DFG is greater than EGF and EGF is greater than DGF, that means DFG has got to be greater than DGF. Okay, DFG is greater than DGF by transitive greater than. Well, what does that do? Well, we now have a comparison of angles within one triangle. That means I can look at the side opposite and say, hey, the side opposite of the greater angle is the greater side, and I can claim that by the converse of the anisosceles triangle theorem. Okay, so I can claim that DG is greater than DF, right? Look at the side opposite of angle G, or this angle DGF, which is DF. Okay, so I can claim that DG is greater than DF now because of the converse of the anisosceles triangle theorem. Why then am I able then to claim that AC is greater than DF? Well, I asked you to mark a step on the previous slide. Step B said, hey, remember that we proved that AC is equal to DG. And now that we have DG greater than DF, I can also claim AC greater than DF, and that is true by substitution. And what we have just done, think about what we just done. We wanted to prove that the side opposite of angle B is greater than the side opposite of angle E, right here, which means we prove that AC is in fact greater than DF. Yes, it's a tricky proof. Okay, it's a long one. But again, it's guided. I will give you all the reasons, or give you all the statements. You provide me the reasons. Alrighty? But there we have it. We've proven the Hinge theorem, okay, which says that if two sides of one triangle are two sides of another, and the angle in between of one is greater than the angle in between the other, then the side opposite of the greater angle is the greater side. Okay, I can claim that AC is in fact greater than the third side there of DF. Now, here's what's interesting about the Hinge theorem. It has a true converse. Okay, so the converse, remember, so the Hinge theorem takes angles and compares sides. But the converse then will take sides and compare angles. Let's take a look at the conditional for the converse of Hinge theorem. It says this: if two sides of one triangle are two sides of a second, recognize that? It's exactly how Hinge theorem starts off. We still have to have a relationship between the two triangles, and that is two sides of one has to be equal to two sides of the other. Has to be. But let's then continue on with converse of Hinge theorem. If two sides of one triangle are equal to two sides of a second, and the third side in the first is greater than the third side in the second, then the included angle of the first is greater than the included angle of the second. In other words, we can now cross-compare angles. Let's bring the converse Hinge, this conditional to life in a diagram. So if you notice, it actually is the same diagram that we used before in the Hinge theorem. However, the approach to this proof is going to be a little bit different, and it's going to be slightly easier. Because we've already proven Hinge theorem, we can take advantage of that. Let's take a look at how our conditional unfolds. So if two sides of one triangle equal to two sides of another, so notice that I've given you AB is equal to DE, and that BC is equal to EF. And AC is greater than DF, so you're already given that the third side of one triangle is greater than the third side of the other. We can claim that the included angle, which is the angle opposite of that third side, is going to be greater than the included angle of the other triangle. So we can claim then that angle B is going to be greater than angle E by the converse of Hinge theorem. But again, any great conditional like this has to be proven. So let's prove converse of Hinge theorem. Let's take a look at how we're going to approach the converse. We're going to approach the converse indirectly. So think about what an indirect proof is. We want to prove, we take our proof statement and we want to negate it. We want to show that every other possibility of our proof statement is false, so that the only remaining thing in our proof statement must be true. Well, our proof statement is that we want to prove that angle B is greater than angle E. So what do we assume? We assume that angle B is not greater than angle E. Well, then by law of trichotomy, there are two other options. Angle B could be equal to angle E, or angle B could be less than angle E. What we have to do in our proof then is contradict both of those. So on the next slide where our proof unfolds, you're going to see that I have to actually contradict both angle B and angle E being equal and angle B being less than angle E. Let's take a look at our reduction then. So our reduction starts off in two parts. Part one, if angle B is equal to angle E, well, then what would then happen? Well, that means, take a look at our diagram. We're assuming that those two angles are equal. Oh, aren't those beautiful? Look at those equal angles there. Man, just lovely. Okay. What then can we say about those two triangles? Well, those two triangles would then have to be congruent by the side angle side congruence, right? Triangle ABC is congruent to triangle DEF by side angle side congruence. Thus, by our best friend CPCTC, AC is equal to DF. Well, that can't happen. That's a contradiction, because in the given, we were told that AC is greater than DF. So Can angle B and angle E be equal? No, that's an impossibility because it reaches a contradiction. Well, there's another possibility. What if angle B is less than angle E? Which now look at angle B. Angle B is clearly smaller than angle E, right? Look at it, obviously. Angle B is clearly less than angle E. Then, by the Hinge theorem, if angle B is less than angle E, that means the side opposite of the lesser angle is the lesser side. Lesser side. In other words, AC is in fact less than DF. But that's another contradiction because we're given that AC is greater than DF, so no way can the possibility of angle B being less than angle E ever be true because it reaches a contradiction. So in other words, it can't be equal to, it can't be less than, which means angle B must then be greater than angle E. And there we have it, the proof of converse hinge. So now we have these two wonderful theorems that actually help us cross-compare triangles. I can cross-compare angles, cross-compare sides with our hinge theorem, and cross-compare angles with our converse of hinge theorem. Let's take a look at a couple examples using the hinge theorem and converse of hinge theorem. So the very first thing you will always have to do when approaching an application of these is verify that the givens of each of the two theorems are satisfied. And the one critical component in both of the givens is that two sides of one triangle are equal to two sides of the other. If we take a look in our diagram below, we're already given one pair of equal sides. AB is marked equal to CD. What I want to do is compare angles 1 and 2. I want to say something that angle 1 is either going to be less than angle 2 or equal to angle 2 or greater than angle 2. So if you notice, I've already got one pair of equal sides, but I need a second pair of equal sides that even remotely begin using hinge or conhinge. Well, notice the two triangles share a side, BC, which means there we have it. I do have two sides of one triangle equal to two sides of the other. Now I can continue on with this cross comparison. Okay, I do have two sides of one equal to two sides of the other. Well, what else am I given? Well, I can compare the third sides. Notice that AC, a length of 2.36, is less than the side BD, 2.37. Well, what does that then tell me? If the side 2.36, which is opposite of our angle 1, is less than the side of our 2.37, which is opposite of our angle 2, I can cross-compare angle 1 and angle 2. I can then officially say that the measure of angle 1 will have to be less than the measure of angle 2. Now, I cross-compared angles here. So which of the two theorems did I use? Hinge or converse of hinge? In this case, I used the converse of hinge. Converse of hinge compares the angles between two triangles, and hinge compares the sides between two triangles. Let's take a look at one more application here. Now let's compare some sides, MQ to JK. So take a look at MQ. This is our side here, MQ, and our third side over here, JK. Well, the very first thing we have to do is remember, are two sides of one triangle equal to two sides of the other? Well, I notice, hey, look, 12 and 12, that's one pair of equal sides. 15 and 15, that's another pair of equal sides. Great. Two sides of one triangle equal to two sides of the other. And I'm given some information about their included angles. Look, 61 degrees, 72 degrees. I can compare angle measures. So since I now can compare, hey, look, angle L is going to be greater than angle P, right? 72 degrees is greater than 61. Then what can I say then about the sides opposite of those two angles? Well, clearly then, if I'm comparing MQ to JK, then MQ has clearly got to be less than JK. Why? Because it's opposite of the lesser angle, right? 61 is the lesser angle compared to 72, which means which theorem did I use to cross-compare these sides? That is hinge. Hinge cross-compares sides, where converse hinge cross-compares angles. All right, we've come to our end of our lesson 5.6 on hinge and converse of hinge. Please be sure to look at the worksheet. If you do have any questions on that worksheet, do not hesitate to ask me via email. With that, be good and do good.